Hi, welcome back to RISC-V assembly one more time, and this time we are going to talk about RISC-V function calls. And we're going to introduce two new instructions that are going to be supporting that. By the way, that'll be about it for the new instructions in RISC-V. All the other ones that we need to complete the base instruction set are just a variance of what we have seen before, and we'll round up all of that up in a bit. So functions in C are very common. In this case, we are looking at an instruction that we may call for multiplication. It's not the very best implementation of multiplication, but it does the multiplication by adding the multiplicand to the product multiplier times. Remember, C calls functions by value. So what it does, it needs to pass the value to the function. Then, so when we execute an instruction, we'll get to the instruction call, to the function call, and that will make us jump to that function. Then we execute the function, and when we hit the return, we go back to the next instruction in the main. If that next instruction is again a function call, we're gonna go and jump again to the function, execute that call again, and return to the next instruction in the code. And keep doing that as many as function calls are there. So what kind of RISC-V assembly code should be used for this? Well, I already said it. These should be different kinds of jumps. So let's get to that. There are 6 fundamental steps in calling a function. The first step, put arguments in place where function can access them. 2, transfer control to function. 3, acquire local storage resources needed for function. 4, perform the function or the tasks associated with it. Then put the return value in place where calling code can find it and restore any registers to their previous state. Release local storage. 6, return control to the point of origin, since a function can be called from several points in a program and program is back in control. I'll give you an example that is not exactly the same but resembles this well. Say you're away to college in normal circumstances, and you go back to visit your parents, assuming that your parents maybe are not that far away. You're in Berkeley and they're in Silicon Valley, so they're not that far away. You go back and you ring the doorbell and they are not there. So what do? You go straight for that planter where you know the spare key is, or perhaps the fake rock from Home Depot where the spare key is. You take the spare key and enter the house. There, you're in control. You acquire the local storage resources, perhaps the refrigerator, and perform the function after that. You raid the refrigerator, but after you're done with the refrigerator raid, you clean up after yourself, because things would not be good if you don't do that. And then you restore everything to the original state, minus the food in the refrigerator, put the key back in the planter such that when your sibling comes back from school, can perform exactly the same function of raiding the refrigerator and cleaning up after themselves before they go perhaps to a soccer practice. Anyway, it's not exactly the same, but it's quite similar to what functions need to do, including the cleanup procedure. All right, let's take a look at what are the RISC-V calling conventions. They're fairly straightforward. First, we would like to use registers because they're faster than memory. We don't want to always have to go to the memory to pass the values. So we are going to be using registers extend to X17 as 8 argument registers. They'll be labeled A0 to A7. And the 2 of them are going to be holding the return values A0 and A1. Return address is going to be stored in register X1, and we are going to call that RA. Also, registers S0, S1, and S2 to S11 are going to have a special meaning of so-called saved registers. Let's take a look at how does a function look like in assembly. So we have a simple function up here in C. It is a sum of two numbers, and then when we call that function, the function will take the arguments, the values of the arguments x and y, and return the sum. Like everything else in RISC-V, instructions are 4 bytes, 32 bits, and each one of them has its own address. Addresses are shown here in decimal values: 1000, 1004, 8, 12, 16. That's where the main program will be stored, and the function may be at a different address, 2000, 2004. So what happens here? When the main is calling the function, what it needs to do is to prepare the things so the function can find them. So first, what we see here, the values A and B are going to be stored in S0 and S1. So we are going to move S0 in A0 and S1 to A1. Those are the ones that are going to be passed to the function. And then we need to prepare for the return. We are going to take the next instruction here, 1016, and put it as a return address in the RA register. Then we are ready to jump to the function. So what we do, we simply jump to the sum. Sum does its stuff, adds A0 and A1, saves the result in a return argument A0, and it's done. Then it's ready to jump back to the main. We use a new instruction here, JR, RA, to return to the value, to the address stored in the RA, which is 1016. Important thing here, we don't use a jump for returning because jump requires us to code up the address value. Function is going to be called from many places in the code, so we better use a variable for that. That's why we use JR. All right. What is instruction support for functions? We actually have a new instruction here. A new instruction, very useful, is called jump and link. So instead of using two instructions to jump to the function, which is saving a value of the next instruction in RA and then jumping to the sum, we can just write JAL sum, and that automatically saves the return address, the next address in the code, in the return, as a return address in X1. So that is very, very useful, very convenient, because first we don't have to think about this next address, and we are supporting the common case. So since this is something function calls are really, really frequently in assembly, we are going to support the common case and execute it fast with a more compact code. Jump and link should probably have been called link and jump, because we first link and then jump. Link is basically forming an address or a link that points to the calling side to allow a function to return to the proper address, to the next address. So we can just use it as JAL function label. Of course, it's called a JAL because it's going to be hanging out in the green sheet with all the other jumps, not with loads. And then the other one that we have seen is JR. There is actually a pseudo instruction that we use as return. Return is JR to return address. So at the end of a function call, we'll generally just find a return or ret. That's basically it for function calls. We have learned how to call a function from C and how does that translate to RISC-V assembly. Just a few notes. There are actually not that many instructions. Several instructions that I mentioned are pseudo instructions because there are special cases of JAL, or yet another instruction here that we are going to see, JAL-R. You can look at this. We don't really need a special instruction for a jump. If we don't save the return address, we put it in X0, that's our jump. Same thing with JAL-R. We haven't learned that, we're going to see it a little bit later, but JR is essentially a special case of JAL-R. That's it for function calls. We are going to see a few examples after this, so see you in just a bit.